And the last piece that we'll put into review for pre-calculus 2 is just solving with trigonometric equations. So for this one up here, I'm just kind of going to keep it basic with the first one, is that if you're told a trig function equals a number, so how we could rearrange this is that we're solving for theta and that we would be taking the inverse sine of 2/5. So that 2/5 that they're giving us, and again, there are a few ways to go about this. If you've been using right triangles, that absolutely works as well. But what I would do is I would think of that as a y coordinate on the unit circle. So if I go ahead and draw my unit circle and just kind of estimate where 2/5 is landing. Let's see, a y coordinate of 2/5, so maybe that's about there. So let's see, for y, we'd have these two locations. And now we're solving equations, so we want all possible solutions. For this specific one, we're just looking for all possible solutions between 0 and 2 pi. So what we can see here is we have two angle measurements. We have this one right here and this one right here. Now, if we keep in mind that when we take inverse sine of a number, and the fact that this isn't one of our special numbers, so we can't necessarily use the unit circle to evaluate this angle measurement, we're going to need to use the calculator. And we'll need to keep in mind as we switch between degree and radian mode that this should be in radian mode because of how they describe the limitation between 0 and 2 pi. If this was in degrees, then you would use degree mode. But since that's radians, we're going to evaluate this in radians. Now, when we take inverse sine with a calculator, it's only giving us values from negative pi over 2 to positive pi over 2. So that means the calculator is going to tell me this angle right here. So if I plug in inverse sine of 2/5 into a calculator, that's going to give me 0.4115. So that's one of our solutions. Theta equals 0.4115. Or you can have the second solution from this green arrow that I drew. Now, what I need to use here are reference angles, and the fact that that 0.4115 is showing up over here, it's just occurring right there. So that right there is 0.4115. So what I'm going to do is to find the green angle, I'm going to use the fact that going all the way over here is 180 degrees, and then I want to go back by 0.4115. So what I'm going to do is go to pi, but then subtract 0.4115. And that should give us a measurement of 2.7301. And then that would be done. Those are all the solutions between 0 and 2 pi, where we would have a y coordinate of positive 2/5. All right, let's do the same thing down here. We're going to stick with that restriction of 0 to 2 pi. What we're also going to do is practice writing those formulas for all possible solutions. Okay. So this first one here, cosecant squared t equals 3. What I'm going to do is change this in terms of sine or cosine, which this relates to sine. So this is 1 over sine squared t equals 3. Multiply both sides by sine squared. I'm just trying to get the sine squared all alone on one side of the equation. And take the square root of both sides. And since we're solving equations, that means so we'll have sine t. And by taking the square root of both sides, we'll have plus or minus this 1 over root 3. Or square root of 1 over 3. You can leave it in that form too. So we have two possibilities. We can have a positive y value or negative y value. And if it helps, you can separate it out that way. It's like we're looking for this angle t such that inverse sine of, and then you could have positive 1 over root 3, or we can have inverse sine of negative 1 over root 3. So on my unit circle, what this is looking like. And if it helps in terms of graphing it, 1 over root 3 is about 0.5. So I'm just thinking of these y values like positive 0.5-ish, negative 0.5-ish. So with that, I'm going to level that out a bit. we end up with two possibilities of positive 1 over root 3. We end up with two possibilities for negative 1 over root 3. So we have these four values coming through, which means in terms of listing between 0 and 2 pi, there are four solutions. So we're going to start listing some numbers for t here. So if I take, and in fact, let me use a different color. So in green, I'm going to have our positive ones. So I'm going to look at those first. So with that, there's this angle measurement right here, which if I plug in inverse sine of 1 over root 3 into the calculator, it's going to give me that value right there. Because that's how inverse sine is limited to that part of the circle. So if we plug in the 1 over root 3, our calculator is going to give us 0.6155. So that right there is a 0.6155. Now, to get the angle that kind of matches up with that, that's also at a 1 over root 3, we would do the same thing that we did up above there. We would go to pi, but then take away 0.6155. So if we plug that into a calculator, that should be 2.5301. And that takes care of this first piece with the positive 1 over root 3. Now for negative 1 over root 3, in fact, we can keep using this reference angle of 0.6155 because, let's see, if I don't have any more colors, here we go. If I go to this angle here, to go there, we would have this positive pi plus, and that right there is our reference angle of 0.6155. You could also get there by taking 0.6155 plus pi. If you see that kind of 180 degrees that's formed, it's the same exact thing. So this is coming from pi plus 0.6155, which would give us 3.7571. And we have one more solution here, and you could, let's see, I ran out of colors, but to go all the way around to there, it's like going to 2 pi, so making the full revolution, but then going back by 0.6155. So we would take 2 pi minus 0.6155. So these were our four cases for using reference angles. If you have that reference angle, if you're in the second quadrant, you do pi minus. If you're in the third quadrant, pi plus. If you're in the fourth quadrant, 2 pi minus that value. And let's see, that'll be a 5.6717. All right, so making our formula, there are, as I've said many times before, a few different ways we can go about this. Let's see, we'll end up needing to describe 4 locations on our unit circle. We can get some nice pairings going. So there's 2 ways to visualize this. And actually, I'm just going to kind of draw a fresh unit circle over here because that got pretty messy with all those angles. Let's see. One way that you can think of the pairings is you could think of those reflections across the x-axis. So like we have these 2 spots that relate to each other. So if I wanted to write those 2 angles, what I would use is that 0.6155. It's just I have the positive version of it and negative version of it. So I can write it as t equals plus or minus 0.6155. And then plus, and then I want those full revolutions about those points. So that would be our period of 2 pi times k. So that we can say 1 revolution or 2 revolutions. We need somewhere to plug in those values. Then we could do the same thing, but for those 2 spots over there, which would be the positive or negative distance there. So if I use that green line from up above, that was our 2.5301. So I could have the positive or negative of that 2.5301 plus 2 pi k to get all of those revolutions about it. Another way we could have done it is, and I mentioned it briefly up above there, the fact that we do have these kind of straight lines coming through. It's like there is this one and this one. So for that blue line, what I could have done, so another possibility for writing this out, or you can write 4 separate equations. You have multiple ways to write these. What I could have done is t equals, and then for that blue line, so that's our 0.6155. And then instead of doing revolutions of 2 pi, what I could have done is just not even revolutions, but distances of pi. So go plus pi, or plus pi again, or plus pi again. Every time I move a distance of pi, I would be ending up back on that blue line. So what I could do is write it as plus pi k. And that would take care of those locations along the blue line. And then for the red line, the same idea of being at that 2.5301, and then any distance of pi away from that value, that would also work. And then so many other possibilities, but I would say those are the 2 key ones to look for there. Okay, that's just one more possibility. There are a lot of others, but okay. One more here with our quadratic, just to get some more practice with these. I chose a fairly messy quadratic here, just so we get this practice. Okay, so since it's quadratic, and I can notice that because I have that sign squared there, along with just standard sign. So with that, I want to get 0 on one side of the equation here. So 0 equals, I want to keep sine squared positive. So what I would be doing is subtracting 9 sine x and adding 2. And that would get me 0 on one side of the equation. All right, then what I want to do is factor this. And you can use trial and error method. You can use the AC method, which is what I teach in my pre-calculus 1 class. Let's just go ahead off to the side here, because if it helps, you can just write it as 4x squared minus 9x plus 2. And let's just throw in a refresher of the AC method. So A, B, C, the AC method says to take A times C, which is 4 times 2 is 8. And then what you do is you look for numbers that multiply to 8 that add up to -9. So that would be a -1 and -8. So some algebra review here. Again, there are a lot of different ways to go about this, but this is one way that's often taught in math classes. So what I do is I use that to split up my -9x. So this is still -9x. I just split it up with a -1 and a -8. And then we can factor by grouping. So looking at that left-hand side there, there's a common factor of x. Looking at the right-hand side, there's a common factor, and it would need to be -2. So I'll make for a positive 4x minus 1. And then I can see I have common factor of 4x minus 1, and the leftovers would be x minus 2. So that's my factored form, and what I'm going to do is just move that over here, but we have sine in there. So I'd have 4 sine x minus 1, and then sine x minus 2. And then we end up with 2 equations. And we solve. So let's see, this will give us add 1 to both sides, divide by 4. Over here, sine x is equal to a positive 2. So this is telling me that we're looking for an angle measurement where the y-coordinate is positive 2, and that can't happen with sine. If we're on the unit circle, we can't have a y-coordinate of positive 2, so that part's not going to give us any information. But over here, solving for an angle measurement with inverse sine of 1/4, this we can solve for. So if I go to my unit circle, This is telling me we have a y-coordinate of positive 1/4, so I'm going to need a calculator to help here. But that should be, let's see, y of 1/4 is maybe about there. So let's say there and there. So I need these two angle measurements. So if I plug in inverse sine of 1/4, that'll give me that red angle there, which is a 0.2527. And then to get our other angle, we can use the reference angle, which would be taking pi minus 0.2527. So x is equal to 0.2527, or pi minus that value, which would be a 2.8889. So those are solutions between 0 and 2 pi. To make my formula, this is a case where I just need to make two separate formulas and then use revolutions at 2 pi around them. So I could have that 0.2527 plus any increment of 2 pi around it, or x is 2.8889 plus any increment of 2 pi around it. And that would do it.